Now we want to look at a certain technique for solving equations known as Euler equations. So Euler equations are equations that look like this. You notice that in each of these, the coefficient of the second derivative is something x squared. The coefficient of the first derivative is something x, and the coefficient of the function y is just a constant. So these are what Euler equations are. And we're going to use a sort of substitution. We're going to use y equals x to the r and see what happens from there. Now here's a summary of what we're about to take a look at. You may want to print this page out for your notebook. So here's how it works. We're going to begin by taking y equals x to the r, which means we need the derivative of that and the second derivative, and then we will substitute those into the differential equation. Now I've got it in brackets here so you can tell what we're substituting. In place of the y double prime, we're going to put r times r minus 1 times x to the r minus 2. And in place of the y prime, we're going to enter r x to the r minus 1, and in place of the y, we're going to have x to the r. We perform the algebra to simplify that. Now, you'll notice that all three terms on the left come out with an x to the r, which we can factor out and end up with the quadratic r squared minus 7r plus 10 times x to the r. Now, one of these has to be equal to 0, so we're going to take the r squared minus 7r plus 10, which is referred to as the indicial equation, and solve it. Now this gives us the sort of roots that we can write our answers from. Now two distinct real roots simply means that our two solutions are c1 x to the 5 and c2 x to the 2. Now in this example, we're going to shorten our work a little bit. Now that you see how the substitution works, we're just going to put that we need the derivative here of x to the r, and we need the second derivative of x to the r. Well, these are always going to be the same thing, and we will shorten this even further in the near future by recognizing that this is always going to happen with an Euler equation. We're always going to have, for example, an x squared and an x to the r minus 2, which when combined gives just an x to the r. We'll have an x to the 1 and an x to the r minus 1, which when combined give x to the r. So that's how we get every term with an x to the r. Now this one, the indicial equation, r squared minus 10r plus 25, has solutions of r equals 5, which is a solution twice. And so, since we have duplicated solutions, our answer then would be a c1 x to the 5, a c2 x to the 5 with ln of x as a second factor. Now in the third scenario, again, we make the substitution, second derivative, first derivative of x to the r, simplify, take the indicial equation, r squared minus 4r plus 20, and solve that. This time you'll notice we come out with complex roots. Well, the two complex roots indicate the solution to the differential equation is a c times x to the 2 cosine 4 times ln of x. And likewise with the sine. Now, other than the added dilemma of solving higher degree polynomials, if we're solving higher order Euler equations, we simply extend the ideas of writing the solutions. I'll show you how that looks. Here are some that we'll take a look at. So when we use y equals x to the r, and this time we'll need the third derivative of that for y triple prime. So the third derivative of x to the r would be an r times an r minus 1 times an r minus 2, x to the r minus 3. So then we will make the substitutions and perform the algebra and get our polynomial, the indicial equation, r cubed minus r squared minus 4r plus 4 is what we need to solve. Now, we can make quick work of these sorts of things by utilizing our Ch18. So if we solve this on a Ch18, we get the three solutions, r equals 1, r equals 2, and r equals negative 2. So again, very similar to what we did with the quadratic, where we had two distinct solutions. We now have three distinct solutions. However, the format of the answer is the same, only this time we have three terms: x to the 1, x to the 2, and x to the negative 2. So again, for this one, we make the substitution y equals x to the r, along with its derivative, second derivative, and third derivative. Perform all of the necessary algebra. Get our indicial equation, r cubed minus 9r squared plus 27r minus 27, and solve that. Again, these are usually things that you can solve if you know how to solve them by hand. Also, you can use your Ch18. So solving this on a Ch18, we come up with one solution, r equals 3, which is 3 times. Now, multiple solutions have this format for their answer. And so we'd have some constant times x to the 3, some constant x to the 3 with an ln of x, and then some constant x to the 3, and then the factor ln of x would be squared. So finally, let's consider this fourth degree and see what happens when we make all of the substitutions. Now again, I'm just indicating that here with the fourth derivative of x to the r. Now, I'll let you work out the details of the fourth derivative of x to the r, but here's what it comes out to be. R times r minus 1 times r minus 2 times r minus 3 times x to the r minus 4. And again, all those substitutions, all of the algebra, multiplying things out, collecting terms, and simplifying, we get the indicial equation r4 plus 18r squared plus 81, which again we need to solve and get the 4 solutions. So we actually have the 2 solutions, r equals plus or minus 3i, which occur twice. Now here's what the format of that would look like. Here we see what we would get for the a plus bi if it were a solution once, and then for it to be a solution a second time, we have, as you can see here, the same thing as that, but with the added factor ln of x.